equations. So let me upload the file related to the previous lecture and explain it for you once again. Lecture. Transform all expressions in the equation to a new form. Okay? So we try to find equivalent expressions for each expression in the equation. Okay, can you see from the book? Now let me bring the topic. 1.6. Okay, one of your friends asked about the process of converting boundary value problems to Fredholm integral equations. I once again explain it using this equation number 107. If you pay attention to the equation, you have a differential equation of order 2. So the differential equation is the second order derivative of y plus y equals x. And we actually need two conditions. And these two conditions are given on our boundaries. One of them is at point 0 and another one is at point pi. Okay, so our conditions are y of 0 equals 1 and y of pi equals pi minus 1. Similar to Volterra integral equation, we try to find for each expression in the equation an equivalent expression. Okay, we suppose that the second order derivative of y equals u. We actually set a new function for the second order derivative. Okay. Yeah. Now, if you take integral from the both sides, you have actually equation number 111 that the integral of the left hand side will be y prime of x minus y prime of 0. Yes, and in the right side you have the integral of u from 0 to x. You don't have the value of y prime of 0 because this is not an initial value problem. This is boundary value problem and you have only the value of function at 0 and pi. So you need to find y prime of 0 using your other informations. Okay? So we continue the process. Once again, we take integral from both sides of the equation number 111, okay? From the left side, if you take integral, you have y of x minus y of 0. From the right side, if you take integral from y prime of 0, you will have y prime of 0 times x, yes? And also the integral of this next, sorry. Okay. The last part is the integral of u, which that you can use the general form of multiple integration for it and obtain that the double integral is equal to the integral of x minus t u to dt. Okay. In this equation, you don't have the value of y prime of 0. But you obtained an equivalent expression for y of x. Do you agree? Okay. So if I set x equals pi in this equation, I will have the value of y of pi. Yeah? Okay. So instead of x, in the whole equation 112, I set x equals pi. What do I have? In the next, in the left side, I have y of pi, okay? And in the right side, I have 1 plus pi times y prime of 0, yes?
Yes.
Plus the integral of pi minus t times u of t from 0 to pi, yes?
Okay.
I have the value of y of pi using my boundary conditions. So I can replace pi minus 1 instead of y of pi, okay? And it will be an equation in terms of y prime of 0 because y prime of 0 is unknown for me. And when I solve this equation, I obtain the value of y prime of 0. When you obtain the value of y prime of 0, you go back to the equation 111. You replace y prime of 0 in this equation and obtain y prime of x using the noun expressions, okay?
Okay.
Then you can replace all of them in the main equation and transform it to a Fredholm integral equation. I don't know if it is clear for you or not. Clear?
Okay.
Did you understand? Okay. Okay, let's go to the new discussion. Before going to the solution of Fredholm and Volterra integral equation, first of all, we review some basic concepts, for example, Taylor series or Maclaurin series that I'm sure all of you are familiar with these topics, but for actually reminding you and to see them in this course and use them in the next actually discussions, we will review these topics. Suppose that we have a function f that is infinitely differentiable in an interval b and c that contains an interior point a. The Taylor series of f generated at x equals a is given by the formula 122. Actually, if we want to compute the value of f at a point near point A, we can use this formula. For example, suppose that you have the value of the function f prime, the second order derivative of f, and the other derivatives of f at a special point, for example, a. So these values are given. You know the value of all order derivatives of the function f at point a. And you are supposed to find the value of f at a point x, which x is in a neighborhood of the point A. This is the point A. You consider a neighborhood of this point. And you know that this x belongs to this neighborhood. You want to find the value of f at this point. For these cases, you can use the Taylor series formula. And if you pay attention, you can see that all derivatives of f at point A are used in this formula. So this is the closed form of a Taylor series. This is the open form when we write down once again the all expression related to each n. We set n equals 0 and obtain f of a. We set n equals 1 and obtain f prime of a over 1 factorial times x minus a. We set n equals 2 and obtain the next expression and continue this process. This is the open form of Taylor series. This is the closed form of a Taylor series. If we set A equals 0, we obtain a special series named as Maclaurin series, and you can see that in the formula of Taylor series we just replace 0 whenever we have A. So the Maclaurin formula will be summation of the nth order derivative of f at 0 over n factorial times x to the power n, because x minus 0 is equal to x. So as I said, this is the Maclaurin series, which is a special case of Taylor series when we consider A equals 0. And this is the open form of Maclaurin series. For example, we want to find the Taylor series generated by the function cosine of x at 0. As you can see, we need the value of all order derivatives of the function at point 0. So we need to compute the formula of derivatives and set x equals 0 and obtain the final value for the derivatives. For different order derivatives of the function f, you know that the function f is cosine of x, so the first order derivative is negative sine of x. The second order is obtained by taking derivative from the first order and is given by a negative cosine of x. And we continue the process. You can see that the terms sine and cosine with negative or positive signs are repeated in this formula. Then for obtaining different order derivatives of f at point 0, we set 0 in these obtained results and compute the derivatives. For the function f at point 0, we have cosine of 0, which is 1. For the first order derivative, when we set 0, we have a negative sine of 0, which is 0. For the second order derivative, we have a negative cosine of 0, which is negative 1. And you can see that we easily continue the process. And all odd order derivatives at point 0, since are actually somehow sine of x, we will obtain 0. But for even order derivatives, since we have somehow cosine of x, we have negative 1 or positive 1. After obtaining these results, so for all n which is, for example, 2k plus 1, which shows that A is odd, we have 0. But the even one are positive 1 or a negative 1, and the sign is changed successively. First one is positive, second one is negative, the next even order is positive, the next one is negative, and so on. So if we replace this value in this formula, we easily obtain cosine of x equals 1 minus 1 over 2 factorial x squared plus x to the power 4 over 4 factorial. Can you tell me the next expression? The next non-zero expression in this formula? Minus x to the power 6 over 6 factorial. Exactly, thank you. So if we want to write it in a compact form, we will have cosine of x equals summation of -1 to the power n over 2n factorial times x to the power 2n. In a similar way, for the function cosine hyperbolic of x, we have 1 plus x squared over 2 factorial plus x to the power 4 over 4 factorial and so on. Because if you consider the function f equals cosine hyperbolic of x, you know that f prime is sine hyperbolics. The second order derivative is cosine hyperbolic, and so on. So we don't have negative signs anywhere. So all expressions will appear with positive signs. Okay? And the closed form can be seen in formula 129. As the next example, we want to find the Taylor series of the function sine of x. The process is completely similar. We write down all order derivatives of the function sine of x, and you can see that the first order derivative is cosine of x, the second order is negative sine of x, the third order is negative cosine of x, and so on. So if we replace x equals 0, we will find f of 0 equals 0, f prime of 0 equals 1, and so on. Now we just need to replace these expressions in the general formula. You can see that for even derivatives, we always have 0. So the terms with even power will be deleted from the expression and the only odd terms will remain. So for sine of x, we have 1 minus x cubed minus x to the power 7 over 7 factorial, exactly, and so on. And this is the closed form of the series. You can see that only the odd expressions remain in the summation. And in a similar way, for the function sine hyperbolic of x, we have a similar expression, but all expressions are with positive signs. Yes, Mr. Muhammad? Where, for your parents or no? Here? Please, the other students, please tell me if you have my voice clearly or not.
Yes, Doctor, clear your voice.
Clear? So this is not my problem, internet connection. Mr. Muhammad, I think you have a problem with the internet. Yeah, did you go to Karbala? Yeah? You are Iran? In dormitory, خوابگاه? He didn't go to Iraq because he told me that he want to go.
This week.
Next week? Okay, so Iranian internet is not good. Okay. Maybe in Khabga, the internet quality is not good. I think so, yeah. Okay, let's continue. And the compact form of the Taylor series, or actually Maclaurin series of the sine hyperbolic of x, can be easily written in this form. Okay. As you saw, for the function sine of x, cosine of x, sine hyperbolic and cosine hyperbolic, you could write the series in a closed form. But in some cases, you can't find a closed form for the related function. But so this always actually doesn't happen to find closed form for a function or closed series for a function. In the next example, we want to find the closed form function for this series. Actually, for these kind of questions, you have to try to find a relation between the number of expressions and the number of index in the summation. For example, when you consider I from 0 to infinity, you have to try to find a relation between, for example, for the I, when I is 0, you have 1. You have to find a relation between 0 and 1. For the next term, you know that you have a coefficient times x to the power n. For the next one, I mean when n or I, consider I equals 1, we have the coefficient equals 3. And 3, you know that 3 is the first order of the function f over 1 factorial. So the first order derivative at point 0 is 3. For the next expression that you have x cubed, you have the multiplication 9 over 2. And you know that this 9 over 2 is the second order derivative at point 0 over 2 factorial. So the second order derivative is 9. So we rewrite, now let me clear the page. We rewrite each expression in a actually ordered form. For example, we write down 1 exactly, 3 times x plus the next one. It can be seen that this 9 can be write as 3 squared. So we can write 3 times x squared over 2 factorial. The next expression actually is these things. We have the third order derivative of 0 over 0 factorial, 3 factorial times x to the power 3. But as you can see here in the denominator, we have 2. And you know that 3 factorial is 3 times 2. So the numerator is somehow that a 3 from numerator and denominator have been deleted. So you have to multiply 3 by the numerator. So we have 27 actually over 3 factorial. So you can rewrite this 27 as 3 to the power 3. And you can finally write 3 times x to the power 3 over 3 factorial. And for the next one, exactly we do the same. And you know that in the denominator you have 4 factorial. 4 factorial is 4 times 3 times 2 times 1. And for being 8, you know that you have to delete 1 3. So you have to multiply 1 3 by numerator, which gives 3 to the power 4. So your expression actually is 3 times x to the power 4 over 4 factorial. And you can easily see that this is, let me write the Maclaurin series for the function e to the power x. For the function e to the power x, you have the Maclaurin series as x to the power n over n factorial. And from 0 to infinity. If you compare this formula with this one, what you conclude? Instead of x in this expression, you actually replaced 3 times x. Am I right? Yeah? So in the left side, I have to replace 3 times x instead of x. So the summation of 3 times x to the power n over n factorial, which is exactly this series, is equal to e to the power 3 times x. So the closed form of this series is e to the power 3 times x. Clear? For the next example, once again, we want to find a closed form for this series. And as I said, you can use some tricks to obtain actually some closed form that you know the Maclaurin series for those functions. For example, here you have 1 minus x plus 1 over 2x squared plus 1 over 6, which is 3 factorial, x to the power 3 plus 1 over 24, which is 4 factorial. Here you have 5 factorial, and so on. So you can rewrite these expressions in a form that you know the closed form of these functions. For example, you know that 1 minus 1 over 2x squared plus 1 over 4 factorial x to the power 4, and all even powers of powers of the term x can be written together. So you know that this series is the Maclaurin series of the function cosine of x, and the next one is the Maclaurin series of the function sine of x. So you have f of x equals cosine of x minus sine of x. Is there any question? Clear? So you got familiar with finding a series for a given function and vice versa. For example, if I give you a series, you have to try to find a closed form for this function. And if I give you a function, you can try to find the Taylor series of that function. You can do the both process. The next section is about infinite geometric series. A geometric series is a series with a constant ratio between successive terms. This means that if you compare two successive expressions in the series, for example, the nth term, an, x to the power n, and the n plus first term, n plus 1, x to the powers n plus 1. If you divide this expression by the previous one, you can find a constant. So there is a constant ratio between successive terms. The standard form of an infinite geometric series is given by this formula. This is actually finite series. I don't know why it was mentioned that it is infinite, because we cut the series when k equals n. So this is the finite geometric series. Okay, this is not correct because we don't have infinity terms. Yeah, so this is not correct. Please make it correct. This is finite geometric series, and the reason is completely clear. We want to have infinite, this n must be infinity. Okay? So the standard form for an infinite geometric series is summation of k from 0 to infinity a k. Oh, this is the geometric, so this coefficient doesn't change. So we have a1 or a times r to the power k. As you see, this is a constant number and you can take this out from the series. So you can write a1 times, it could consider it as a for making it more simple. So you have 1 plus r squared plus r cubed plus etc. So an infinite geometric series converges if and only if the absolute value of r is less than 1. So if we have a infinite geometric series, for having this series as a convergent series, we have to have this inequality. Actually, the absolute value of r must be less than 1. Otherwise, this series diverges. The sum of infinite geometric series for r with absolute value less than 1 is given by, as I wrote, you can write it here as A1 times 1 plus R plus R squared plus, and the expression in the parentheses is 1 over 1 minus R. So S equals A1 over 1 minus R. And let me say that if we have n instead of infinity, what will happen? So this is not correct to consider it with index n. This is S and it goes to infinity. When we have the finite geometric series, let me write it here. Actually, the summation of, for example, A times R to the power K from 0 to n, we have A1 plus A1R plus A1R to the power n, and if I factorize from A1, we have A1 1 plus R plus R to the power n, and you know that here the expression in the parentheses is equal to 1 minus R to the power n plus 1 over 1 minus R. So this is the finite geometric series. So this is not correct. We have actually infinity, and the infinity series is equal to A1 over 1 minus R. But in the finite series, you have A1 times 1 minus R to the power n plus 1 over 1 minus R. And you know that when you take the limit from Sn, when n approaches infinity, you will have S. And in this case, when you approach n to infinity here, so let me take limit from the expression A1 times 1 minus R to the power n plus 1 over 1 minus R. You know that this limit, when n goes to infinity here, since the absolute value of R is less than 1, then the limit of R to the power n plus 1 will be 0. R is less than 1. Okay?
But finite number is 1.
No.
Less than 1.
No. For example, 1 over 2.
Yes. Between the 0
Between 0 and 1. Or in other words, the absolute value of 1 over 2 is less than 1. Okay?
Yes.
Take limit of 1 over 2 to the power n when n goes to infinity. What will be the result? Let me write it here if you see from the phone. Limit of R to the power n when n approaches infinity with R less than 1. For example, when you compute 1 over 2 to the power n. When n goes infinity, what will be the result?
Infinity upon infinity.
Infinity? Really?
Upon infinity. It's
What?
0.
0. Why? Because you have this limit 1 over to the power n, yes?
Yeah.
And when n goes to infinity, here you will have infinity and 1 over infinity is 0. Okay? So if you replace any r less than 1, you have limit of r to the power n. When n goes to infinity is 0. Okay? So if you replace a1 times 1 minus r to the power n plus 1 over 1 minus r, if you replace this limit here, you will have a1 times 1 over 1 minus r, which gives this finite form of this series. Yeah.
Okay.
So this section of book has some mistakes. Please make them correct. Here you have actually S if you want to have infinite geometric series. When you say infinite, it means infinity. So you have infinity here and the last term should be deleted because this summation should continue. You have the finite form as a1 times 1 minus r to the power n plus 1 over 1 minus r, but infinite form is a1 over 1 minus r. Okay, let's go to the example number 1. We want to find the summation of the infinite geometric series when we have the terms 1 plus 3 over 5 plus 9 over 25 plus. If you divide each successive term, you can find the ratio or constant ratio. For example, by dividing 3 over 5 by 1, you have 3 over 5. By dividing 9 over 25 over the previous number, which is 3 over 5, you obtain 3 over 5. And if I continue the process, you can see easily that each successive terms has a ratio 3 over 5. So this is a geometric series with ratio 3 over 5. And since it is a infinite series, you have to use this formula. The term A1 is 1. So you have S equals 1 over 1 minus 3 over 5. And if you compute the term, you will have 5 over 2. Okay, the next example, once again, is a infinite geometric series. And for finding the ratio, you have to divide two successive terms. For example, here you have negative 1 over 3 and the first term is 1. So the ratio is 1 over 3, negative 1 over 3 over 1, which is negative 1 over 3. The next two expression, you have 1 over 9 over negative 1 over 3, which by dividing you obtain negative 1 over 3. Yeah, And if you divide the two next successive terms, you obtain -1/3. So this is a infinite geometric series with ratio -1/3, and the first term, A1, or the multiplication of each term, is 1. So we have this series equals 1/1 minus -1/3, which gives 1/1 plus 1/3, and the result is 3/4. And you, if you pay attention in both examples, you have the ratio. Somehow the absolute value of this ratio is less than 1. You have to check this matter always to write the result. In the next series, we do the same, but first of all, we rewrite this summation somehow that we can see a geometric series in it. So you can see that this x cube doesn't have any regularity with respect to other terms. Okay, so we take it away. We write down the expression x cube, but the other terms, all of them has a same factor, x/5. So we factorize from x/5, and we see that from this term we have 1, from the next one we have 1/3, from the next one we have 1/9, because we take 5 out of this series. Okay, so we can write it in this way. And now for this series in the parentheses, we actually have a geometric series with constant ratio 1/3. Am I right? We have a geometric series with constant ratio 1/3, and we can use this formula for finding the equivalent expression. So for the term in the parentheses, we have 1/1 minus 1/3. This is 2/3, and the result will be 3/2. So we multiply these 3/2 times by x/5 and have the result as actually x cubed plus 3 times 2 times x. Let me check. Here you have 1/1 minus 1/3, which gives 2/3. Yeah, is it correct? And the result will be 3/2. When you rewrite it, you have x cubed plus x/5 times 3/2. Please check if I'm doing in correct way or not, because as I saw, the result is different from what the book was written. Here you have 1/1 minus which is 3/3, so gives 2/3, and by reversing the result we have 3/2. So the result will be x cubed plus 3x/10, which is different from what the book gave. Okay, so please make this result correct, because it I think it forgot to write 1/5. Yeah, when you compare this result and this one, you can see that this 5 was misplaced. So please make it correct. the book forgot to write this 5 in the denominator, and the result is not correct. So the final result will be 3/10 times x. Okay. Let's continue. Do you have any question? Is there any question? No? Okay, let's go to the next example. In this example, yeah, Mr. Manzar, do you have any question?
No question, Doctor. Thank you.
Okay. Yeah, let's continue. In this example, we want to simplify this expression. We have s, as you can see, 1 plus pi over 8 secant of x squared plus pi over 16, once again, secant squared. So if you compare two successive terms, you can see that here, from this term to this term, we have this expression completely similar. So you need to divide pi over 16 times secant squared of x over pi over 8 secant squared of x. And if you divide these two expressions, you find 1 over 2. If you do the same for the two next successive expressions, once again you find the ratio 1 over 2. So we write down this summation, we keep this one and take factor from the actually similar expressions in all of them, which is pi over 8 times secant squared of x, and in the parentheses for the first expression after 1 we have 1, for the second one we have 1 over 2, for the third one we have 1 over 4, for the next one we have 1 over 8, and we know that in the parentheses we have an infinite geometric series with ratio 1 over 2. So for the result of this parenthesis, we have 1 over 1 minus 1 over 2, which gives 2. And you have to multiply these 2 by the term pi over 8, which gives 4 here. So we have s equals 1 plus pi over 4 secant squared of x. Clear? Okay. And I think this is the last example of this section. Yeah. The last example, you have the summation of these expressions. You can see that if you write the terms down, you can see that from the third term, we have a regularity in our expressions. You can see that in all of them, the numerator is 11, but the denominators change. Somehow, if you divide two successive coefficients, you find that 1 over 5 is the ratio in these series. So we have S equals x to the power 4 plus 1 over 14x squared. These two expressions doesn't have any regularity with respect to the others, so we write down the same thing. From the next expression, we have the similar factor 11 over 17 times x squared, and if we apply the factorization process, we have 1 from the this term, we have 1 over 5 from the next term, we have 1 over 25 from this term, and you can see that the expression in the parentheses is an infinite geometric series with ratio 1 over 5. And you have 1 over 1 minus 1 over 5 for the result of the expression in the parentheses, which gives here you have 4 over 5, and if you reverse it, you have 5 over 4. So you have, let me check. Here, I think I wrote it correct, but the result once again here is completely different. So we have x to the power 4 plus 1 over 14 x squared plus 11 over 17 x squared times 5 over 4. This 5 and this 17 can be simplified, and here we have 12. Yeah, so the result will be x to the power 4 plus 1 over 14 x to the power 2 plus 11 over here we have 12 times 4, which is, no, this is, let me check it. It is when you divide 17 by 5, you have 14. Yeah, I think this is correct. Okay, 14 times 4, which is 56 times x squared. And you can take same denominator from these two expressions, and the result is x to the power 4 plus 15 over 56 times x squared. Is there any question?
No, thank you, Doctor.
Okay.
Thank you, Doctor. No question.
Okay. All the concepts that we have reviewed were about introducing the basic concepts in integral equation discussion. For example, introducing Fredholm integral equation, Volterra integral equation, singular integral equation, integral differential equation with different types, Fredholm actually, and Volterra, and all the necessary perimeterally concepts in integral equation. In the next chapter, I mean chapter 2, we will concern just about Fredholm integral equations, about their solutions, how we can solve these equations, or to check that if there are some analytical methods for solving this kind of equations, and the other topics related just to Fredholm integral equations. And in chapter 3, we will have the same discussion for Volterra integral equations. So since these equations are actually different, the behavior of confronting with these equations or introducing methods for these different kinds of equations will be different, and we will discuss about them in 2 different chapters actually. Okay, let's review a little about the actually Fredholm integral equation, and we will leave the main topic for the next lecture. As you know, the general standard form for Fredholm integral equation of the second kind is, as you see in equation number 1. For being Fredholm, we have to have constant bonds for the integral, and as you see, we have A as the lower bound and B as the upper bound of our integral part. We have the kernel K. This lambda is a constant parameter, and you can see that the unknown function u appear inside the integral and outside the integral, and it makes this integral from the second kind. And also, if we have the function f as a non-zero function, we have non-homogeneous or inhomogeneous second kind Fredholm integral equation, and if the function f is 0, we will have homogeneous integral equation. And also, if we don't have this function u outside of the integral, we will have Fredholm integral equation of the first kind. So we will discuss about different situations of Fredholm integral equation and about the methods for solving this kind of equations. We consider 2 different scenarios for the kernel K. In some cases, we suppose that the kernel K is actually separable, which we will define further. And by considering this property, we will introduce some methods for solving this kind of equations. So, as you can see, we call a kernel K as a separable kernel if we can write this kernel as a summation form. And if you pay attention, you can see that you have in each actually expression, you have a function just in terms of x and another function just in terms of t. So since we separate the variables x and t completely, we call these kind of kernels as a separable kernels. So as you see, it's correct that our function k is a bivariate function. But if you pay attention, you can see that these variables are completely separated. So we call them separable actually kernels. For example, here, these are some examples of separable expressions or kernels. You have x minus t, you have x plus t, you have xt. Xt you can consider just one term in the summation, and you can consider j of x is x and h of t is t. So this is a separable kernel. You have here x squared minus 3 times xt, and you can see easily that here you have x squared times 1, so the function in terms of t is 1, plus negative 3x times t plus t t squared. And you can see that this is completely can be written in this form. So these are some examples of separable kernels. And another concept for some special kinds of kernels, the kernel K is defined to be square integrable in both x and t in the square, x in the interval a and b, t in the interval a and b, if the equality number 3 satisfies. So if we have this integral less than infinity, we say that this kernel is square integrable in terms of x and t. So when we see these two expressions, separability and also square integrability, you have to remember that this condition and this condition are satisfied. We have a very important theorem for Fredholm type integral equation that is called Fredholm alternative theorem that relates the solutions of homogeneous and non-homogeneous Fredholm integral equations. So we explain about this theorem. The non-homogeneous Fredholm integral equation, this equation, which we considered as the general form of Fredholm integral equation, has one and only one solution that states the uniqueness of the solution. If the only solution to the homogeneous Fredholm integral equation, this one, actually f of x is 0, is the trivial solution u of x equals 0. So if this homogeneous integral equation has only the solution u of x 0, we can conclude that the corresponding non-homogeneous equation, this equation, has a unique solution. So if you want to check the uniqueness of the non-homogeneous integral equation, you have to check if the corresponding homogeneous integral equation has just the solution. You know that if you replace 0 here, the left side you have 0, and in the right side you have 0. So it can be easily that always 0 is a solution of homogeneous integral equation. But we have to check that this is the only solution for this equation, because there may be other solutions for this integral equation. So if we check the uniqueness of this solution, trivial solution 0 for the homogeneous one, we can claim that the solution of the non-homogeneous integral equation is unique. The rest of matters are very theoretical, so I will leave them for the next lecture. For today is enough. If there is any question, you can ask. Okay, the question? Is there any question? You are welcome.
Thank you, Doctor.
Okay. Thank you all. Have a good day. Bye.
Thank you, Doctor. Bye.